Hi, welcome back, superstars. Today you're with Zach, and we will be covering AP Chemistry 1.1, which is moles, concept, and conversion. So first of all, we'll be covering why are moles used by chemists. So moles are used to make a connection between a given amount of particles and a defined mass. So think of it as different substances will have a different defined mass that these amount of particles are connected to, and I'll be going over that in the next slides. So another thing is a mole of any substance will always contain 6.022 times 10 to the 23 particles. And you can also think of moles as like a unit of measurement. And a really like a real world application or connection you can use to remember them or remember the concept is that they're like a dozen, where a dozen is always 12 of something. So here on our next slide, we more so go into what I said last slide about how despite every substance's moles having 6.022 times 10 to the 23 particles, they will have different defined masses connected to that. So I'll get into that in a minute. But first of all, questions may refer to molecules, particles, ions, or atoms, but they generally all mean the same thing. And there's always 6.022 times 10 to the 23 of them per iteration in the question. So also, what you like, a big important thing is you need to make sure you pay attention to defining factors, such as if a molecule is diatomic or it doesn't fully dissociate, and especially states of matters of your sample, which will be gone over later in the video. So as previously mentioned, molar mass is the mass in grams of a substance that contains 6.022 times 10 to the 23 particles, or 1 mole. So why that can be different is why the molar mass of substances can be different is because let's say you have carbon with a molar mass of 12.01 in comparison to hydrogen with a molar mass of 1.01. 6.022 times 10 to the 23 particles of carbon will have 12 times the mass of the same amount of particles of hydrogen, just due to their mass. So another thing to remember is the molar mass of a substance is equal to the atomic mass, but in grams. And since we know the atomic mass of carbon is shown on the periodic table, which is also the same for every other element, it's shown on the periodic table, generally at the bottom, but in this image it's at the top. We see that the atomic mass of it is 12.01 AMU, and we can translate that to a molar mass of 12.01 grams. So some formulas we will use are moles equals particles over 6.022 times 10 to the 23 particles per mole. And since that constant is becoming sort of a mouthful, it's also known as Avogadro's constant or Avogadro's number. So I'm going to be referring to it as that for the rest of the video. And our next formula is molar mass, which is measured in grams per mole, is equal to mass in grams over moles. You can also derive different formulas from these two to determine other values, like your mass or your amount of moles and your amount of particles. So now we're going to get into a pretty elementary example of application of the concepts you just learned. So remember that a mole of a substance is equal to 6.022 times 10 to the 23 particles. And let's start with this question. So determine the molar mass of hydrogen chloride in its gaseous state and the amount of hydrogen and chlorine atoms in a 10-gram sample of hydrogen chloride. So our molar mass of hydrogen is 1.01 grams per mole, and our molar mass of chlorine, well, atomic hydrogen and atomic chlorine, is about 35.45 grams per mole. So when we add these two numbers together, since hydrogen chloride just has one hydrogen atom and one chlorine atom, you just You don't have to multiply these by anything, so you just add them together, and you get a molar mass of about 36.46 grams per mole. Okay, so now that you have your molar mass of hydrogen chloride, what we can now do is apply this 10 gram mass, so we can use one of the formulas we used earlier in the video. So the formula we used earlier in the video was moles, or right now I'm going to write moles as an N. So moles equals mass, which is our little m, over molar mass, which is our 2 m's. So our mass of our sample is 10 grams, so the numerator should be 10, and we established that the molar mass of our sample is 36.46 grams per mole. So now we divide these numbers to determine the moles of our sample, and we get about 0.274 moles HCl. Also, please excuse my bad handwriting. It's pretty hard on a mouse. Anyways, now to determine the amount of particles or molecules of hydrogen chloride we have, we would multiply that by Avogadro's constant. So you'd multiply that by 6.022 times 10 to the 23. And what you get is, from that multiplication, I'm going to notate that number. Oh, here, sorry. I'm going to notate that number as a capital A, just for the sake of time and writing. The number you get in particles of HCl would be about 1.65 times 10 to the 23 molecules. Sorry. So, as we previously established when we looked at the chemical formula for hydrogen chloride, we have one atom of hydrogen and one atom of chlorine in each molecule, meaning that we have to multiply this number by 1 or just not multiply it at all, because since we have our amount of molecules, now we can determine the amount of atoms of each part of the sample. So basically, since both of these are only 1 in the chemical formula, all we have to do is just rewrite this amount. So you have 1.65 times 10 to the 23 atoms of hydrogen and chlorine. So next question kind of brings in a new concept. But first of all, you're given the molar mass, so you don't necessarily have to calculate for that, which is a pretty nice time saver. So you have your 98.08 grams per mole, and you're going to divide that by your 10 gram sample, the same way we did in the last question to determine moles of your sample. And you should get about 0.102 moles of your sample. And now we can multiply that by the Avogadro's constant, and we should get about 6.14 times 10 to the 22 molecules. So we're at the same point we were in the last question, where now let's look at our chemical formula, because this number gives us the amount of molecules of our sample, which is hydrogen sulfate in its gaseous state. So when we look at this, we see that there's 2 hydrogen atoms and 1 molecule of sulfate per molecule of hydrogen sulfate. So what we're going to do, that's a little bit of a bigger step than last question, is now you have to multiply this number by 2 to determine your amount of hydrogen atoms. because you have two hydrogen atoms in each molecule of the substance. But since we have the same amount of sulfate molecules in the, like, we have just one sulfate molecule per one sulfate molecule per molecule of the sample. Sorry, that was kind of a mouthful. Your atom or your molecules of sulfate should be the same as your molecules of hydrogen sulfate. So the last question is a little trickier, and some keen observers or people who are just coming to this video to like review past concepts in AP Chem may realize that something's a little off about this question. So pause the video and try to do some like thinking, see if you can pick up what's wrong, and I'll go over that in a second. Okay, so now that you've hopefully thought about it, or you kind of have no clue what I'm talking about, but that's totally fine. We're looking at a sample of hydrogen fluoride, but it's in an aqueous state of matter, meaning that we'll call it hydrofluoric acid as of right now. So normally what you would do is you divide your grams over molar mass to determine moles, and then multiply that by Avogadro's constant. But this question's a little different, and this is what I meant in this previous slide, where I said pay attention to certain defining factors like state of matter or if something fully dissociates in a solution. So this is an example of that. So hydrofluoric acid, if you have already taken chemistry, or you're just like here to review, or you just have general knowledge of acid and base, hydrofluoric acid is a weak acid. And the meaning of a weak acid is that it won't fully dissociate in a solution of water. So we won't be able to necessarily determine the quantity of H plus and F minus ions found in our sample when dissolved in water without a given volume, because you'd need to use Ka-based calculations, which are a little more advanced, and we'll get into them in the future when we cover acids and bases in later units. But this question was kind of a trick question, just for you to like realize that state of matter is a super important factor, and it can completely change the answer and course of how you're going to answer a question. So that was it for this video about 1.1. May have been a little simple for some viewers, but these earlier chapters are kind of just a review of what you learned in past chemistry classes. So please feel free and feel encouraged actually to leave comments, suggestions, questions, concerns regarding the topic, video, or channel's future. And please remember to tune in next time for some more awesome chemistry content. I wish everyone a great day, and definitely keep studying chemistry. It gets better from here.